Most media coverage of the Strait of Hormuz focuses on a single image, a tense military coordinate and a fragile corridor responsible for 20% of the global oil supply. Below the headlines lies a surreal physical reality. This is an island of salt mountains and red clay canyons, where temperatures can melt human will, and fresh water is more precious than gold. By conventional ecological measures, the conditions in this corridor are so extreme that biological systems should completely fail. Survival here is an engineering problem. This civilization persists by turning the island's most lethal constraints into functional tools, a masterclass in engineered mechanisms designed to bypass the limits of the land. Summer water temperatures in the Gulf regularly reach 96 degrees Fahrenheit. In almost any other part of the world, this level of thermal stress triggers mass bleaching and the death of entire reef systems. The reefs around Hormuz have endured thousands of years of extreme thermal cycling. This exposure killed off less resilient individuals, leaving behind survivors with a degree of heat tolerance encoded directly into their biology. On land, the air temperatures frequently exceed 122 degrees. At this threshold, conventional ventilation fails, making the interior of a standard building uninhabitable. In coastal villages like Loft, residents rely on an ancient architectural solution, the Badgir wind towers. This diagram illustrates how these structures function as passive climate control systems. The open mouths capture the prevailing breeze, while internal baffles channel that air downward. As the air moves through the mud brick channels, it cools, creating a survivable microclimate below. From the heat-tolerant corals to the Badgir towers, the logic remains consistent. Centuries of iteration have produced a set of mechanisms designed to neutralize lethal heat. Finding fresh water and nutrients in a hypersaline, soil-choked environment is a fundamental biological challenge. The Hara mangroves survive through a biological mechanism refined across millions of years. Their roots filter out the lethal saltwater, while the leaves physically expel the excess salt in visible crystals. This filtration process creates the nutrient-rich conditions that support the fish and shrimp populations of the wider Gulf, functioning as a nursery for the entire region. Humans developed a parallel system for managing scarcity. In coastal villages, a network of 366 ancient wells was rotated so that each well was used only once per year, preserving freshwater reserves that the environment cannot replenish. The locals even integrate the harsh geology into their diet, using the iron-rich red clay, known as galak, as a dietary staple and seasoning. In Hormuz, environmental scarcity acts as a forcing function. It drives life to absorb the extreme geology and utilize it for its own sustenance. The shallow coastal waters and surrounding sea impose a severe geographic isolation on the islands of the strait. To navigate these waters, boat builders rely on lenge vessels. These ships are built entirely from inherited spatial memory, passed from father to son, without the use of written diagrams or specifications. On the water, the sun reflecting off the salt creates intense UV exposure. The Bourget mask developed as a practical barrier to protect the skin from severe damage during a lifetime of outdoor work. Over generations, this environmental shield became a social text. The specific patterns and construction of the mask now communicate a woman's marital status, family lineage, and regional origin. This isolation also preserved the Kumzari language. It is a linguistic fossil record, constructed from fragments of Persian, Arabic, Portuguese, and Hindi left behind by passing empires. These traditions, from the construction of a ship to the vocabulary of a village, function as refined survival technologies, forged by the specific pressures of the Gulf. These biological and cultural adaptations operate on a slow, steady timescale. Today, they are colliding with the rapid influx of modern industrial pressures. Oil contamination from tankers, marine warming that outpaces coral genetics, and international shipping regulations are dismantling the systems that have sustained life here for millennia. Ancient survival mechanisms are breaking because the speed of modern threats outpaces the biological and cultural speed of adaptation. When an environment's nursery or a culture's encoded knowledge is compromised, the collapse of that system is total and irreversible. These fragile local systems exist in the same geography as the global energy architecture, with 21 million barrels of oil passing over them every day. Lethal heat, resource scarcity, and the need for extreme resilience have been the ordinary terms of existence in Hormuz for centuries. These same conditions are now becoming the global standard. The Strait of Hormuz offers a blueprint for an era defined by instability. It leaves us with the question of whether we are paying attention to how life persists when the margins disappear.